Light technologies, getting ready. Why does your face look distorted when it is reflected in a shiny silver spoon? How do we see things? And last, how does a telescope work? In the distant reaches of space, stars are being born, slowly forming out of clouds of gas and dust. The Orion Nebula, shown here, is one of the stellar birthplaces. Young, hot stars release huge amounts of energy into the cloud in which they have formed, causing the cloud to glow. With the help of powerful telescopes, astronomers can see these clouds of gases as a glowing mist or nebula spreading out through space. Other scientists keep their focus at very close range. Compound light microscopes allow biologists to see tiny structures such as the bacteria shown in the micrograph on the next page. In this chapter, you will find out how we see things and how our understanding of light and its behavior has helped us build optical devices that extend human vision. Spotlight on key ideas. In this chapter, you will discover 1. How light behaves when it strikes curved, reflecting surfaces such as concave and convex mirrors. 2. What a lens is and how it works. 3. The difference between a real and a virtual image. 4. How an optic system works. And 5. How human eyes, cameras, telescopes, binoculars, and microscopes form images. Spotlight on key ideas. In this chapter, you will create different kinds of images using lenses and mirrors. Determine how lenses are arranged in telescopes, microscopes, and other optical devices. Number 3, role play the parts of a system that involves input, output, and feedback. Design and build simple optical devices. And last, number 5, design an experiment to determine whether an image is real or virtual. Concave and convex mirrors. Have you ever looked at yourself in the bowl of a spoon? See figure 8.1. Figure 8.1, what kind of image is reflected by the bowl of a spoon? How did the image look? Was it upright or upside down, inverted? The attitude of an image describes whether the image is upright or upside down in relation to the object. Was the image large or small? Did the image change when you looked at the underside of the spoon? Figures 8.2a and b show the two main types of curved mirrors. Each type can form images with different attitudes and sizes. You used both types of mirrors in the starting point activity. The concave mirror curves in like a cave entrance. The bowl of a spoon is concave. So is the palm of your hand. Astronomers' telescopes often use concave mirrors. A shiny sphere and the underside of a spoon, on the other hand, are examples of convex mirrors. When you did the starting point activity, you saw that a curved mirror could create images in different places. Sometimes the mirror would project an image in front of it. At other times, it appeared to form images of various sizes behind the mirror. Why does a curved shape form an image so different from the ones that you see in a plain mirror? Find out in the next investigation. Figure 8.2a. A concave mirror is curved like the inside of a shiny bowl. Figure 8.2b. A convex mirror bulges outward like the surface of a shiny, helium-filled party balloon. Images formed by curved mirrors. A concave mirror can produce two types of images. If an object is close to the mirror, the image seen is upright and larger than the real one, as in a plane mirror. The image looks as though it is located behind the mirror. Mirrors for shaving are often concave in shape because they are meant to be used at close range. On the other hand, when the object is far from the concave mirror, the image is inverted and smaller than the real objects. Convex mirrors are more common than concave mirrors. Convex mirrors always produce small upright images as shown in figure 8.3. Figure 8.3. The image formed by a convex mirror is always small and upright. Because the image of each object is smaller in a convex mirror, you see more of the overall scene. This characteristic is applied in security mirrors in stores. See figure 8.4. Figure 8.4, convex mirrors, the ones that bulge out, are useful security devices. These mirrors allow one person at the counter to see most of the customers in the store. Parking garages sometimes have convex mirrors to allow drivers to see if an oncoming car is just around the corner. Convex mirrors are also used as side view mirrors on cars. See figure 8.5. With a convex mirror, the driver can see several lanes at once. However, the image is small. That gives the impression that the cars seen in the mirror are far away, when they are in fact much closer than they appear. You can see that the shape of the mirror determines its properties and its uses. The next time you see a curved mirror, try to picture how the light rays are reflecting in order to form the image that you are seeing. You will also see them on roadways around sharp bends, so that you can see if any cars are coming on tight turns where there's a lot of foliage. Lenses and vision, one of our senses. Knowing how curved mirrors reflect light can help you understand how lenses affect light rays. A lens is a curved piece of transparent material such as glass or plastic. Light refracts as it passes through a lens, causing the ray to bend. A concave lens is thinner and flatter in the middle than around the edges. See figure 8.6. Figure 8.6. Light refracts when it travels through lenses. The double concave lens shown on the left causes light rays to spread out. The double convex lens shows on the right brings light rays closer together. So the double concave lens is divergent. It's a divergent lens, where the double convex lens is convergent. Light passing through the thicker, more curved areas of the lens will bend more than light passing through flatter areas. This causes rays of light to spread out or diverge after passing through the lens. A convex lens, also shown in 8.6, is thicker in the middle than around the edges. This causes the refracting light rays to come together or converge. Lenses and images. Lenses are probably the most useful and important of all optical devices. Eyeglasses, for example, were made from lenses as early as the 19th century. The type of lens used in an optical device determines whether the image is real or virtual. An image forms when light rays from an object converge. The light rays spread out from points on the object. A convex lens refracts these rays so that they come back together. See figure 8.7. A convex lens causes parallel rays to converge. Why do the rays from the lens on the right converge farther from the lens compared to the rays on the left? However, the lens directs light from the left portion of the object to the right portion of the image. Similarly, light from the top of the object is directed to the bottom of the image. See figure 8.8. Thus, an image formed by a convex lens is sometimes inverted rather than upright, because your eye sees the image of the flower by light rays that are actually coming from the image. The image is real. An image on a movie screen is a real image, since light actually travels from the screen to your eye. Any image that can form on a screen is a real image. Both film projectors and overhead projectors use convex lenses to create real images. Let's read 8.8, figure 8.8. Images formed by a convex lens are inverted and upside down. Now below, in some cases, light rays only seem to come from the image. Do you remember the bird and the mirror in chapter 7? The bird is convinced that its friend is on the other side of the mirror, but there is no other bird. Light rays are coming from the friend as if they had started from behind the mirror. In fact, the rays are just bouncing off the mirror, so a virtual image is produced. Light rays do not actually come from a virtual image. See figure 8.9. Figure 8.9. Computers are sometimes used to create effects called virtual reality. This digital composite image shows a biochemist using a virtual reality system to investigate molecular interactions. In what way are the computer effects virtual? Plain mirrors always produce virtual images. Remember that if you cannot form an image on a screen, the image must be virtual. Sometimes a convex lens can be used to produce a virtual image. For example, a magnifying glass is a convex lens used to produce an enlarged virtual image. Finally, concave lenses produce virtual images from real objects. Concave lenses are used in combination with convex lenses in cameras and telescopes. As the following section explains, they are also used in eyeglasses to correct a vision problem known as nearsightedness. Knowledge of how light behaves when it travels through lenses helps eye specialists to correct vision problems. As figure 810b shows, a convex lens placed in front of a far-sighted eye helps bend the light rays so that the image appears on the retina. As figure 810c shows, a concave lens placed in front of a nearsighted eye moves the image back, so that again it forms on the retina. Comparing the eye and the camera. There are many similarities between the human eye and the camera. See figure 8.11. A comparison of the camera and the human eye. Study this diagram and try to infer the function of each part of the camera and the eye. You already know that you see objects when light is reflected to your eye, refracted through your lens, and focused on your retina. In a camera, the lens refracts the light and the film senses the light. Explore how a camera works in the next investigation. Then, read the pages that followed for a more detailed comparison of the eye and the camera. Putting it in focus. In a camera, if an object moves closer to the film, the lens must move farther from the film to keep the image in focus. This is what you do when you focus the camera. In the human eye, you cannot move the lens farther away from the retina. Instead, the ciliary muscles change the shape of the lens. Refer back to figure 811 on page 247. If the object you are looking at comes closer to you, these muscles make the lens bulge in the middle. This keeps the image in focus on the retina without having to stretch the eyeball. The process of changing the shape of the lens to adjust for different object distances is called accommodation. That's 2 C's and 2 M's. As people become older, the lens stiffens and loses its ability to change shape. It can no longer become thick enough to focus on close objects. As a result, many people wear convex lenses as reading glasses. The shortest distance at which an object is in focus is called the near point of the eye. The longest distance is the far point of the eye. For the average adult human eye, the near point is about 25 centimeters away. See figure 8.12a. Here's somebody reading a book. Most adults can focus on objects that are about 25 centimeters away. However, babies can focus on objects only about 7 centimeters away. See figure 8.12b. The far point is said to be infinity. After all, a person with normal vision can see the stars, and they can be many thousands of light years away. Bringing in the light. If you are photographing a scene and a cloud suddenly covers the sun, the brightness of the scene decreases. As a result, the amount of light reaching the film decreases. If the light is too dim, the film will not receive enough light to record the image clearly. In this case, the camera's diaphragm and shutter can be adjusted to allow the correct amount of light to reach the film. The diaphragm is a device that controls the aperture, the opening, of a lens or optical system. The shutter is a device that limits the passage of light. The aperture in the diaphragm can let more light into the camera by being opened wider, as shown in figure 8.13. The shutter can let in more light by staying open longer. So 8.13, the diaphragm controls the amount of light that enters a camera. The opening in the diaphragm is called the aperture. So the opening is called the aperture. Small aperture, small opening for photographing a bright scene. Large aperture for photographing a dimly lit scene. In the human eye, the iris, which is the colored ring, kind of gives your eye character, functions like the diaphragm of a camera. See figure 8.14. If the light is dim, the iris increases the size of the eye's opening to let in more light. This opening is called the pupil, which appears as the dark center of your eye. Figure 8.14, the iris controls how much light enters the human eye. The natural adjustment in the size of the pupils is called the iris reflex. You are generally unaware of this reflex, which is extremely rapid. What happens when you first walk into a dark movie theater on a bright, sunny day? You are probably unable to see anything at first. The split-second iris reflex is the first in a series of adjustments the eye makes to enable you to see the interior of the theater. When you leave the theater and walk into bright sunlight, the opposite reaction occurs. The sunlight glare makes your eye feel uncomfortable. However, the iris reflex quickly shrinks the size of the pupil. Less light enters the eye, and other adjustments take place so that your eye feels comfortable again, seeing the image. At the back of the camera, you will find the film. The image is focused onto this light-sensitive material. The light energy causes chemical change in the film to record the image. In the human eye, the retina senses the light. When the cells in the retina detect light, they create small electrical impulses that travel from the retina to the brain through the optic nerve. The point where the optic nerve enters the retina does not have any light-sensing cells. This point is known as the blind spot. You can easily demonstrate the presence of your blind spot by following the steps outlined in figure 8.15. Note that each eye sees what the other misses, because the blind spots are not in the same place. Figure 8.15, locating your blind spot. Hold this book at arm's length. Cover your right eye with your hand. Stare at the X while you move the book slowly towards yourself. The dot should disappear and then reappear as its image moves onto your blind spot and then off again. The parts of the camera are contained in a rigid, light-proof box. See figure 8.16. Cameras differ in size and complexity, but the parts of all cameras are housed in a rigid, light-proof box. In the eye, layers of tissue hold the different parts together. In order to keep the eye from collapsing, the eyeball is filled with fluids called humerus. See figure 8.17. Figure 8.17, the eye is an almost spherical object that is filled with fluids. And then you have the parts of the eye, the vitreous humor, which is the fluid in the eye. You have the lens. You have the little pupil there. That's on either side of the pupil is the iris. You have the cornea, the ciliary muscles, etc. In addition to keeping the eye rigid, humerus help refract the light that enters the eye. The next investigation will refocus what you have learned about the parts of the eye and the camera. Did you know contact lenses are very thin lenses placed directly on the cornea of the eye? A thin layer of tears between the cornea and the contact lens keeps the lens in place. Most of the refraction occurs at the air lens surface. And there you have the contact lens covering the cornea and a tear fluid system between the contact lens and the cornea provides stability. Extending our vision. Human knowledge about our planet and the universe was very limited until we developed tools to extend our vision. We now have the ability to peer into the tiny world of microorganisms and out into the vast reaches of outer space. The tools we use for these inquiries seem quite different from each other, but they are based on the same understanding of light, mirrors, and lenses. Telescopes. Telescopes like the one shown in figure 8.18 help us see distant objects more clearly. In a refracting telescope, light from the distant object is collected and focused by a convex lens called the objective lens. A second lens called the eyepiece lens works as a magnifying glass to enlarge the image. See figure 8.19a. A refracting telescope uses a convex lens to gather and focus light. A reflecting telescope uses a concave mirror to collect rays of light from a distant object. The mirror is called the primary or objective mirror. It forms a real image, which is then magnified by the eyepiece lens. See figure 8.19b on the next page. Let's just look for just a moment. It says telescopes like the one shown in figure 8.18 at the beginning of where it says telescopes. Let's go to the observatory down below. Figure 8.18, the Mauna Kea telescope, jointly sponsored by Canada, France, and Hawaii, is located near the summit of Mauna Kea an extinct volcano in Hawaii. It uses a concave mirror that measures 3.6 meters in diameter. What does a concave mirror do to light? And then 8.19a, a refracting telescope uses a convex lens to gather and focus light. So here's the eyepiece. The light's coming in the other side, of course. So you have light from the distant object, and you have the objective lens, and then a real image of the distant object is formed. Okay. Let's look at 8.19b, which they mentioned on the previous page. A reflecting telescope uses a concave mirror to gather and focus light. They generally tend to be very thick, very wide. And you can see how the light is coming in and it's going to bounce back and form an image up near the eyepiece because the light is reflecting up. The lens in a refracting telescope and the mirror in a reflecting telescope both act as a collector of light. Reflecting and refracting telescopes must have a large collector, either a lens or a mirror, in order to gather as much light as possible from the distant object. The collector then focuses the light into an image. As you learned in Conduct an Investigation 8b, the farther the image is from the lens, the greater the magnification. Similarly, the farther the image is from the mirror in a reflecting telescope, the greater the magnification. For the greatest magnification, the telescope needs to have as large a distance as possible between the object being viewed, a star or a planet, for example, and its image. This explains why some telescopes are so enormous. Binoculars. Binoculars are actually two reflecting telescopes mounted side by side. You can imagine how difficult it would be to hold up two long telescopes. In binoculars, the telescopes are shortened by placing glass blocks inside. These glass blocks, called prisms, serve as plane mirrors. Rather than traveling down the long tube of the telescope, light in the binoculars is reflected back and forth inside a short tube, as you can see in figure 8.20. 8.20, binoculars use prisms to reflect light. Cool tools. Prisms are used to reflect light in a device known as a heads-up display, or HUD. Light reflects through prisms to make an image appear in front of a person's eyes. This device helps airline pilots who need to check airspeed and altitude while at the same time looking out the plane's windscreen. Pilots can monitor the glowing displays projected in front of them, even as they watch the approaching runway. HUDs have also been developed for scuba divers. The device is positioned inside the diver's mask. The diver can check depth, water pressure, and air consumption by examining an image on this data projected directly in front of the diver. This spares the person the inconvenience of having to check the readings on separate gauges that indicate depth, pressure, and the amount of air left in the diver's tank. What else do you think HUDs could be useful for? Microscopes. As you learned in Chapter 1, a magnifying glass is simply a kind of microscope. Effective magnifying glasses can magnify objects up to 10 times their normal size. A compound light microscope can magnify up to 2,000 times. See figure 8.21. Like telescopes, compound microscopes have an object lens that forms a real image of the object and an eyepiece lens that magnifies the image further. As you also learned in Chapter 1, compound microscopes use more than one lens in the objective and eyepiece to improve the sharpness of the image. See figure 8.22. To be sure, a classic-looking microscope. Figure 8.22, a compound light microscope, uses several lenses to magnify an object. Figure 8.21. Microscopes are used to probe the world of cells, bacteria, and other living things too small to be seen with the unaided eye. This laboratory technician who carries out fish hatchery research for an Ontario Ministry of Natural Resources is scanning a tissue sample for signs of disease in fish.